Hello and welcome back. We have here a problem which says a 40 kg block of aluminium is at 450 Kelvin. It is thrown into a lake. That's a lot of effort to throw it in. The temperature of water in the lake is 283 Kelvin. The block attains an equilibrium with the lake water after some time. Calculate entropy change for the aluminium block, entropy change for the lake water, and total entropy change during the process. So let us look at this problem. It will also possibly give us some new concept which we can discuss after doing it. So we have 40 kg block of aluminium. So the mass of the block is 40 kg. Substance is aluminium. The temperature initially for the aluminium is 450 Kelvin. It is thrown into a lake. So we have this aluminium and this is water. Temperature of water in the lake is 283 Kelvin. The block attains an equilibrium with the lake after some time. Calculate the entropy change for the aluminium block, delta S for the lake water, and delta S total. This is what is asked. So we have a 40 kg block. Presumably the lake is very big. So if we throw a block of aluminium into the lake, this is at higher temperature, but it's going to fall deep into the lake. We'll assume that there is no appreciable change in the mass of the lake. This temperature is higher than the boiling point of water, but let us assume for a moment that no water is boiled out. Did you want us to assume that? We did not want us to assume that. Okay, let us assume that some water is boiled out because we can find out how much is.
Lake is very big, so no temperature change in it.
Yeah, but locally some stuff can evaporate before it goes. So, but anyway, so I think Sumit and Ankit do not want us to assume any boiling of water because the lake is very big. So they say, let us assume that the water of the lake does not change in temperature, which is a reasonable assumption. Even if some little water boils out, it will be very small compared to the mass of the lake and volume of the lake. So that's quite all right. So what we would see is that the aluminium is cooling down. Its final temperature would be equal to the temperature of water in the lake, which is 283 Kelvin. For the water itself, this could be assumed to be essentially an isothermal process because it's a huge mass and volume of water. We do not expect any change in the temperature of the water after this process is complete. So we need to find out how much is the change in entropy. We have the TdS relationship. We'll start from there. For a solid, we know that this is essentially negligible. So we are left with this. We know that this can be written as C times dt, Cv times dt. We are missing the value of the specific heat capacity of aluminium, which is required for this problem. I am told that we can take it as 0.9 kilojoule per kg Kelvin. This should have been given there, that's all right. So we see this, so we can see, sorry, this is capital, okay, this is small ds because I am not writing mass over here. But I have the mass of the block, so let me write it as T capital ds is, this would have been capital U, so this is m into C into dt. So d capital S is m into C into dt by t, which on integration gives us m, assuming Cp is constant, m is anyway constant, ln of T2 by T1. So, that is 40 kg into 0.9 in 10 to the power 3 joule per kg Kelvin into ln of T2 is 283 and T1 is 450. Which gives me a value of minus 16.69 into 10 to the power 3 joule per Kelvin. We see that this value is negative because essentially the aluminum is losing heat. Our convention is that heat lost is negative. Therefore, when we lose heat, del Q by T is also negative because T is always positive, del Q is negative. So, there is a change in entropy which is negative. So, the entropy of this aluminum block is coming down because it is losing heat. Now, we can calculate, we are asked to calculate essentially delta S for water. The water is undergoing an isothermal process. Temperature is 283 if I remember correctly Kelvin. So, for the water we can again use the TdS relationship. We could do this, or in the case of the water, so there is no change in the temperature of the water. So, this expression is not really useful to us, but in the case of the water what we can assume is that because it is an isothermal process for the water, we can assume that any heat which is transferred to the water is reversible because it is undergoing an isothermal process. So, if we were to assume it in that way, then what we can do is that for the water we can say that TdS is equal to del Q. The amount of energy got by the water must be whatever is lost by the aluminum block. So, the aluminum block was giving out an amount of heat. So, magnitude wise whatever is given by aluminum should be del Q for water. Of course, our convention is that this is negative and this would be positive. So, that is something we need to take into account because it is heat gained and heat lost in one case. So, for the aluminum in terms of magnitude this is essentially mc into it is dt which is d final minus d initial, and this would turn out to be negative for the aluminum. This is 40 kg into 900 joule per kg Kelvin into 283 minus I think we had 450. Which gives us a value of about 6 megajoules. We get minus 6 for aluminum. For water, heat transferred to the water is 6 megajoules. So, using this expression and assuming heat transfer to the water to be reversible because the water is at constant temperature, we get essentially ds is del Q by T or delta S is essentially 6 in 10 power 6 divided by 283. This is a constant. So, on integrating we just get, sorry, this is again d capital S because I have capital Q over here. So, this implies del capital S is Q by T after integrating. So, we get this value as 21.2 kilojoule per Kelvin. So, if we find out, so we are asked to find out entropy change for aluminum block, which is here, entropy change for the lake water, which is here, and total entropy change for the process, which is essentially entropy change for the universe. So, we get this value as 4.5 into 10 to the power 3 joule per Kelvin. So, what we see is that the aluminum block loses heat and cools down. In the process, it also loses entropy. The water gains heat, its temperature does not change. In the process, it has an increase in entropy. And if we look at the entropy change for the aluminum block and the entropy change for the water and we sum them up, we see that this value is positive. This is quite interesting. So, if we look at say work, we saw that if you have two objects and there is work interaction between them, the work interaction is positive for one, negative for the other. If we sum them up, it is 0. If we look at heat interaction, if we have two objects, heat interaction happens with transfer of energy between the two objects. There is reduction in energy of one, increase in energy of the other. If you sum up the heat interactions, it is positive in one case, negative for the other. If you sum them up, it is 0. But when you look at entropy, what we see is that if you have reversible processes, then if you sum up the change in entropies of the two objects, then the sum is 0. Where if you have irreversible processes or most processes, if you sum up the change in entropies of the system and its surroundings, the sum does not become 0, the sum is greater than 0. So, we can actually show this in terms of the laws we have, and we will do it in a bit, but this is essentially what we refer to as the principle of increase of entropy. So, what we see is the only way to reduce the entropy is essentially to transfer out heat. So, if I have an isolated system, which means I cannot transfer heat because an isolated system is something which is insulated and the mass is fixed, then for that kind of a system, since I cannot transfer out heat, the entropy cannot reduce. So, we can also rephrase some of the concepts we have discussed so far in saying that the entropy of an isolated system will always increase, or more correctly, an entropy of an isolated system cannot decrease. It can either remain the same or it can only increase. And similarly, since the universe, if we take the entire universe, since that is an isolated system, what we can say is that the entropy of the universe cannot decrease. If everything which happens in the universe is reversible, then the entropy may remain constant. But we know that things are not reversible because we know, for example, if I rub my hand, we know it's an irreversible process because there is friction. If we know that when the air is flowing, it has viscosity, which makes it irreversible, and so on. So, therefore, what would be correct for us to say is that the entropy of the universe always increases, which is also in some way paraphrasing the second law and Clausius inequality and so on.